Okay, I count it a blessing myself to be doing this. My PhD thesis was primarily writing a finite element code back about 40 years ago. And I'll have a little bit to say about that a little later today. But my assessment is that the finite element method is one of the most powerful tools that a person in science has, and certainly engineering, in the engineering field. And most engineers, I think, don't grasp the power of the method. They may apply it, but as far as the bigger picture is concerned, many I think don't understand just how powerful it is, especially in light of how much computer resources we have today. And so I want to begin by, well, let's first of all, let me just mention that originally Dr. Cho, who got his PhD under Mark Horstmeyer last spring, was scheduled to be the instructor. But he had this opportunity to be a guest, a visiting scientist at Yale for the next 9 months. And I considered it such an opportunity, I volunteered to cover the course, to teach the course in his place so that he could take advantage of that opportunity. He's working under one of probably the top mineral physicists in the world. And that professor's interested in Hitchin's work because of the internal state variable approach that he's brought for Mississippi State. He's applied that, which historically has been applied mainly to metals. Hitchin has now applied it to silicate minerals that make up the earth, the interior of the earth, the mantle of the earth. And so I think as I share a little bit more, you'll understand why I consider that development to be so strategic, so important. And I want to help him make it. There's a lot of competition to get research funding from agencies, and being at Yale will help him. I'm hoping he will be able to make some connections and get onto that track of starting to fund his own research. This course is, as you know, on the finite element method. And some of the main course objectives, before I get into these, let me just say that the PowerPoints that I have, that I'm using, are mainly those that Mark Horstmeyer, Dr. Horstmeyer, has used since I believe around 2011 in teaching this class at Mississippi State. So he offered, Dr. Horstmeyer offered me to allow me to have access to these materials. So much of what we're going to be doing is based on his the course that he's put together over that period of time. However, today I'm adding some new twists to it. So as far as the objectives, I haven't changed these from what he had. Let me see if I can get my pointer to work. some of the main objectives of the course is to master the basics of finite element analysis. And I'm really hoping that you all will nail it. You will come away feeling like you have ability to apply the method to whatever problem you might encounter. So I'm hoping you'll come away with a lot of confidence about understanding the method and actual skill in applying it. So part of that is understanding the assumptions behind it and the sources of error that are present, so that you can apply the method wisely and correctly. And we're going to put a lot of emphasis on actually using existing finite element analysis software, in particular Abacus. And so we'll spend some time, have some tutorials, have some hands-on experience with Abacus, which is a commercial, some pieces of commercial software that's widely used on a wide variety of applications. What Mark is interested in, and also including, is what he's calling advanced finite element analysis, where the material properties can be nonlinear, where you really have a good handle on the errors that are there. We not only do statics problems, but dynamic problems and multiphysics problems. And there's going to be quite a bit of emphasis on constitutive models and implementations of those models. Basically, if you're modeling some kind of continuum body, if you don't have the correct constitutive model of how the material deforms under stress, your calculation may be close to worthless. So it's crucial that you understand the constitutive model, and that you are using the one that's appropriate to your problem. And Mark has spent his career working on those issues. And then we're going to have hopefully look at examples, some state-of-the-art applications of the finite element method. So as I already mentioned, the finite element method is incredibly powerful and also highly versatile in modeling the physical world. And there's really almost no limit of the things that it can model. It can model things that mechanical engineers design, like this, I guess it's a transmission assembly, and looking at all the stresses that can arise in that kind of system.